Okay, so let's return to the lecture course. So what are we doing? Well, what we've been looking at is distributions associated to the normal distribution. So basically, one of the things that we were looking at are these two new types of distribution called the chi-square and the t-distribution. So let's just remember what is a chi-square distribution, because we're going to use it in a moment. The idea is if you had a sum of squares of IID standard normal naught 1 random variables, and you have n of them, and then basically that gives you a random variable which is chi-squared. Okay, so the chi-square distribution basically is a probability density function. Where is it written? Has a probability density function which looks like that. It's just a special case of something called the gamma, and it's a kind of random variable which is non-negative. And so where we left off at the end of last week was, well, a couple of results, just to remind you, because we're going to see this result a couple of times today. So if you remember that if you take the variance of an estimate, so the estimate of the variance s squared, so just in case you've forgotten what it is, so I'm going to see this in a moment, s squared is this quantity here, this one here, it's just the sample variance of a collection of IID random variables, okay, with the normalization 1 over n minus 1. So remember that thing, when scaled by n minus 1 and divided through by the variance of each of the observations, is chi-square on n minus 1 degree of freedom. So that's one of the last theorems that we left off with. Okay, so that's just a revision of some of the things that we saw at the end of last week. And in fact, we covered this slide, but I think this is a convenient place to pick up our conversation. So we're going to talk about the t-distribution, which is another distribution which is associated to the normal and in fact the chi-square distribution. And we're going to use this result explicitly later on today, I think, for establishing confidence intervals. Okay, well, let's not worry about that for now. So we suppose that z is standard normal random variable, that is, this means 0 and variance 1, and independently u is a chi-square random variable on n degrees of freedom, and we define a new random variable capital T, which is just defined to be the ratio of z divided by u over square root of u over n, okay, where u is this chi-square. Now this new random variable t, which is real values, so remember z is real values and u is non-negative, so I can take a square root of it. So t is also non-negative, sorry, is real valued, and it's set to this random variable on the right, which is defining t, is precisely called a random variable which is t distributed. And we remember that we looked at this PDF of this random variable. So the PDF has this kind of functional form, okay, which might look a little bit mysterious, but the key point is that you can understand that it's t, the value of the random variable gets larger and larger. Of course, this function goes to 0, okay, but the rate at which it goes to 0 is much slower than a Gaussian. So basically, you can see, it's not very well illustrated on here, but basically the amount of probability in the tails of this distribution is more than a Gaussian distribution, if especially n, the degrees of freedom of the chi-square, is especially small. Okay, so that's the key point. So we commented, basically it looks like a Gaussian with heavier tails. This result, which we had noted was a mistake, there should be a z in here. And basically, as the number of degrees of freedom, little n, grows very large, then the associated distribution of the random variable t essentially becomes Gaussian-like. Okay, that's one can prove this formally if you like. And basically you can have a look at the tables of the value of this the survivor functions. The probability that t is greater than or equal to t, which is the integral between little t and infinity of the PDF, and is given in a statistical table. Okay, so we have the tables this time, so I didn't have it last week. So there's a typo on this slide, by the way. There's not my side. So this is the table, hopefully, that you'll be given in the exam. This is what my colleague has given me. And basically, this is this t table, which you can see in the top left, computes the probability that t is greater than or equal to t sub q is equal to alpha, I guess. So basically what this thing is computed, there's only 4 of you here today, so we can just use a board. So what it's basically computing, you have a t distribution, so you have t, you have ft of t, okay, and you have your PDF, which is symmetric about 0, okay, and so this area here, this is alpha, and this is the value tq, and this is the PDF, so here t is t distributed on q degrees of freedom. Okay. Oh no, on let's say the v degrees of freedom. Okay. So what does this table do? Well, along the top of this particular row gives you the value of alpha, i.e. the size of this tail probability, and this column here refers to the degrees of freedom, so that's the number of chi-squares, okay, and then this gives you the value of, on your, in this case, t-axis, which gives you this point, such that the probability to the right of that point is exactly alpha. So for instance, if you look at the notes, the first one is correct, luckily. If you want to find, so you say the degrees of freedom is 10 and alpha is 0.05. What is the value of t? Well, you can get it from the table. So what do? I go to t, I go to 0.05, and so this value here precisely is 1.8125, and so that's the value on this t-axis, which precisely gives you the probability that you're bigger or equal to 1.8125 is equal to 0.05. Okay, that's what he's got, 1.812. Okay, so the second one is actually a little bit wrong, because if you check the table, it's not the same thing. But if you check the table, so I take the degrees of freedom 10, but I take the tail probability alpha is 0.01. Okay, so t is 10, and now I get 0.01. Then the actual value of t, this little t, is 2.7638. So that's not the value that he has here. Right, this is 2.602. It's not correct. Okay, so that's basically how you use the table. So this statistical tables, has all of them. So this one has the t. It's going to have the chi-square, which we discussed last week. I have 2 tables for that, but this is the same one essentially. This is the and this is the standard normal one. And there's one more called the f, which we will talk about very soon. Okay, so that's basically how you use the table for the t distribution. Hopefully it's not too challenging on that particular table. Excuse me. So there's also some facts which are also particularly useful, is that the expectation of the random variable t for any number of degrees of freedom little n is 0. Okay, and this is kind of, well, it's not obvious, but basically we know that the PDF is symmetric about 0 and has a modal value there. So the average value of the random variable is 0. The variance is intrinsically related to the degrees of freedom and is n over n minus 2, obviously only defined if n is strictly bigger than 2. And what's the interesting point here? Well, the interesting point here is as n, the degrees of freedom get smaller and smaller, so the tails of the probability distribution get heavier and heavier, to the extent that when n is 2 or less, the variance of the random variable is actually infinity, i.e. there's basically no second moment for this random variable, which indicates how heavy the tails are. Okay, so this is a kind of interesting feature of this probability distribution. Of course, this calculation, well, it's not that hard to do, but we're not going to do it today. So you're just told this fact. Okay, and this is how you can use an Excel. I'm not going to go through that. I think that you can do that yourself. Okay, let's just make a remark before we move on to the last part of this collection of notes. If you have a random sample, so x1 up to xn, IID, and they are normally distributed, we know already that we have this result, which is based upon, well, this is exact actually, that if you take x bar, so the x bar, the expectation of each random variable is mu, and the variance of each random variable is sigma squared, then we verified this thing last week, that this random variable is precisely Gaussian with 0 mean and unit variance. Okay. Okay, and now if I defined, we know from our theorem 5.5, that's what I just talked about at the beginning of this afternoon session, that n-1 scaling the estimate the variance divided by the true variance is chi-square on n-1. Okay, so it can be shown. So this is well, is beyond the scope of this lecture, of course, that these two random variables z and u, by proxy of the fact that x bar and s square are independent random variables. Okay, and what does that mean? Well, it's interesting because basically if I define t is equal to x bar minus mu over s over root n, which is precisely just the ratio of z and u. Okay, so I divide z by u. What I have is this is z and this is u, and I take z over square root of u over n. So this is z. I divide by the square root of u over n minus 1. Sorry, this is n minus 1, chi-square n minus 1. So then basically this thing is normal naught 1. This one is a square root of a chi-square divided by its degrees of freedom. And so this is obviously equal to z over square root u over n minus 1. And by the fact that we said at the beginning that the definition of a t distribution, remember the definition from the beginning, this is what we started, is that if z is normal naught 1 and u is chi-square and n degrees of freedom, and I divide by the square root of u over n, then I define a t. Okay, so in this scenario, the interesting point here is that here z and u are independent normal naught 1 and chi-square n minus 1 degrees of freedom, and the statistic t, which is x bar minus mu over s over root n, is then t on n minus 1 degrees of freedom. Okay? And why is that interesting or significant? Well, basically we're going to use this result later on to derive confidence intervals and t-tests. Okay, so probably when you were studying statistics at school, you probably saw these t-tests, and this is basically where it comes from. Okay? Right, okay, let's have a look at an example, and then we'll move on to the final part of this lecture notes, which are on the F distribution. So the example runs like this. You have a manufacturer of light bulbs, and basically this manufacturer believes that on average the light bulbs burn for 500 hours on average. Okay, now in order to work out or to look about to kind of investigate, I don't know if maintain is the right word, to investigate this average, this individual tests 25 bulbs each month, and if this computed t value falls between t minus 0.05 and t 0.05, this individual is satisfied with this claim. So the question is the following: what conclusion should be drawn from a sample that has a mean which is of 518 hours and a standard deviation of 40? Okay, and we assume that basically the distribution of the burning time in hours is approximately, or let's say it's normal. Okay, so the world that we're in is this statistic here. Okay, so we're going to have a random sample x1 up to xn, which are going to be normally distributed with a mean mu and a variance sigma squared. And we're going to compute the statistic and see what happens. Okay, essentially. Right. So now, first of all, what's the sample size in this case? So in this statistic, this is what we're going to use. The sample size at little n is 25. That's the number of bulbs that this person tests. So little n is 25, so n minus 1 is 24. So these values now, we need to find t minus t 24 on 24 degrees of freedom, and the probability is 0.05. Okay, so what this statement means here is that basically, in this case, you have a t distribution on 24 degrees of freedom, okay, and then this area is alpha, and this alpha area is alpha, and it's alpha is 0.05, so it's like a 90% confidence interval. Okay, so now what we need to do is define those values little t, which give a probability to the left and right of 0.05 respectively. Okay, so we have our table, so we can have a look. So we have now, here 24 degrees of freedom. So it's not very easy to read this. So 24 degrees of freedom, so this should be 1.71. And that's what it is, 1.71. So this value is 1.71. Now remember that this function is a symmetric function, so if the probability to the left of 1.71 is 0.05, then the probability to the left of minus 1.71 is also 0.05. Okay, so the point is that this value, 1.711, that's been verified from our table. You can just about see it. I'm sorry, it's a little bit small, but basically you can see this is the column which is 0.05, and this is the row which is 24. Okay, so that's where there's 1.7. He must have a different table to me because it's 1.71, 1.709. Okay, so you can just about see it here. So like I say, just one more time, that's what you've got that value, and repeating myself, here this is area is 0.05. By virtue of the fact that this function is symmetric, the point here minus t, which is minus 1.711, also has a probability that the left is 0.05, and that's what he's talking about. Okay, so that's where those numbers come from. Okay, so now basically, to finish off the question, this manufacturer is happy if the statistic essentially lies in this interval minus 1.711 and 1.711. Okay, so now what we are told that this person thinks the mu is 500. Okay, so now what we're going to do is going to compute our statistic, this one, which is t distributed on 24 degrees of freedom, under the assumption of the question. Okay, so now remember the mean which we see is 518, mu is 500. We're also told, that the standard deviation is 40, and the sample size is 25, so the square root of 25 is 5. Okay, so this is just 18 over 8, which is about 2.25. So the actual value of this statistic lies actually in the tail. Okay, so basically what does this mean? Well, under this distribution, right, this hypothesized distribution, so this statistic, as I said, this statistic here in our scenario is supposed to be t distributed on 24 degrees of freedom, okay, but what we're saying is the value that we realize of this statistic is really right out in the tail. It's actually quite an unlikely value for us to see. So what that means is that basically the value of mu is actually a little bit larger, should be a little bit larger than the one that this individual is hypothesizing. Okay, so where is it there? So that's my confusing. Okay, so basically the point is that the statistic is outside the range, so this manufacturer, based upon this particular type of criterion, is actually being a bit under-optimistic about the associated value of the length of the average length that the light bulbs would last. Okay, so this is what this sentence means here, that basically the manufacturer, based on this particular test, has basically been under-optimistic. Okay, the products are better than this person thought. Okay, so let's just finish off now this chapter with our final special distribution related to the normal distribution, well, indirectly in this case, because it's related to the chi-squared. Okay, so the distribution, the F distribution, is another non-negative random variable, and is defined in the following way. So we did U and V, random variables, which are independent chi-square random variables on n1 and n2 degrees of freedom respectively. And we define the random variable capital F as the ratio of U, that's chi-squared on n1 degrees of freedom, divided by its degrees of freedom, divided by V over n2, where n2 is the degrees of freedom of V. Okay, that's a definition. So this is indirectly related to the Gaussian because the U and V are random variables which depend upon the Gaussian distribution by the sum of squares of n1 in IID Gaussians. Okay, so this is basically a random variable which we define in this way, and it's called an F distribution. It's related to the Gaussian. Okay, one can derive the PDF of this random variable f. It looks like this. It's basically, it's not trivial to find this equation. Actually, you have to do a bit of work, but that's basically what it is. Okay, and so that can be derived actually by something called a change of variable argument, but we don't cover it. It looks horrible. Remember these gamma functions, if you've forgotten, or I never mentioned it today, that the gamma function is just this special function, which is only known for a few values, including the integers, non-negative integers. Okay, so that's the PDF. What we're going to do now is to see where this distribution is of interest. And again, it's of interest. It's going to be of interest in the context of hypothesis testing and confidence, well, hypothesis testing really. So we have the following notion. So we have two random samples. Okay, that means a collection of pair of independent random variables. So IID random variables which are independent of each other. The first is of sample size n1 and the second is of sample size n2, and they're Gaussian. So remember, just in case you forgotten what this thing means, just to keep it clear in your mind so that basically you always know what this random sample means. I'm just going to write it down so that we get clear what this first paragraph, this first bullet point means. Basically is that you can say x1 ... xn1 are IID normal with some mean mu1 and some variance sigma square 1. And independently, let's say independently, y1 ... yn2 are IID, independent, identically distributed normal with mean mu2 and variance sigma squared 2. Okay? So basically that's what that first bullet point means, so independent, identically distributed. We know from the result that we have quoted right at the beginning of the lecture, right? So remember at the start of the lecture, I reminded you of this result that we talked about at the end of sorry, I've gone too far. I told you at the end of at the start of this lecture, sorry, I lost my train of thought. Okay, so basically, where is it gone? Yes, this one. So basically n-1 s square over sigma square is chi-square on n-1. So in this case, if you take either of these samples, they're IID Gaussian with mean mu1 or variance sigma square 1 and sigma square 2 respectively. So if I do n1 minus 1 times s squared over sigma square 1, that's basically a chi-square. So the theorem, what the theorem says, if you like symbols of mathematics, is that basically, if I say that the variance is sx squared, and I multiply it by n minus 1, and I divide by sigma squared 1, then this one is chi-square on n1 minus 1 degrees of freedom. Okay? And respectively, this one, independently, if I take sy square times n2 minus 1 over sigma squared 2. Okay, so s square x is supposed to represent the variance. This is chi-square on n2 minus 1. Okay, this is what basically the result that we're going to appeal to. Okay, if you like these symbols, they make it clearer for you. If not, you could just read the notes. Sorry. Okay, so that's basically, so that's this u and v. Okay, so those things that I've written towards the left of the board is just u and v if you can't read them. And they're independent random variables. They're independent chi-square n1 minus 1 degrees of freedom and chi-square n2 minus 1 degrees of freedom. So they're independent. Okay, and what's the interesting point here? Well, the interesting point here is precisely from our definition of the F distribution. If we now take u and v as defined on the previous slide and scale them by the degrees of freedom respectively, then basically this thing, okay, and so remember u is basically n1 minus 1 s1 squared over sigma squared 1, and respectively v is n2 minus 1 s2 squared over sigma squared 2. So of course these two factors, they cancel, and we get this ratio, which is basically the ratio of the variances S1 squared to sigma squared 1 over S2 squared over sigma squared 2, and that's F distributed, and the 2 degrees of freedom are N1 minus 1 and N2 minus 2. And again, the significance of this, the significance of this statistic is for to be used as a test for equality of variances of two different samples of different sample sizes. Okay, we're going to see that in the next chapter, I think. Okay, so an important result, which is basically useful because it's going to allow us to determine values from the table. We're going to have a look at F tables in a moment. So if F is distributed with N and M degrees of freedom respectively, and I take the random variable 1 over F, then 1 over F is F distributed with degrees of freedom M and N. Okay, so if I take this one, I've got N and M. Basically, I do the inverse of this, 1 over F, and I get M over N. You just flip around the degrees of freedom. Okay, and it can basically be found by, immediately, yes, you can find it immediately, right? It's pretty straightforward to establish this result. I mean, if you're interested, why is it the case? Let me just tell you why. It's very simple. So as it says, it's straight from the definition of the F distribution. So remember that by definition, I can justify this point if you want. There we go. So this is the definition. So we define, in this case, F, which is equal to a chi-square, we'll call it U, divided by N degrees of freedom, and independently V is a chi-square on M degrees of freedom. So by definition, capital F is a F distribution on N and M degrees of freedom. Now, if I consider the random variable 1 over F, well, 1 over F, so that implies, this equation implies that 1 over capital F, well, I've just flipped the ratio around. I have V over M on the numerator and U over N on the denominator. Okay, and so by definition, the ratio V over U over M, where U is a chi-squared on M degrees of freedom, N degrees of freedom, and independent V is a chi-squared on M degrees of freedom, gives me precisely that 1 over F is a F distribution on M and N degrees of freedom respectively. Okay, so that's why this theorem is true. There's not really anything to prove there. And we can find values of the F distribution, that is to say probabilities from the tables. Okay, so let me just interpret what this statement means with a bit of a graph. Remember that the F distribution is a random variable which is non-negative precisely because of the definition, right? U and V are non-negative random variables. Okay, so what does this statement at the bottom mean? And then we'll just draw it out, and then we'll think about how do we get these numbers that are quoted. So the F distribution, so it depends on the degrees of freedom. I suppose it looks something like this. So here I guess we go for the F, and this is the PDF, I don't know, F, capital F of F, or maybe it looks, I don't know, like this. Okay, and then basically, if we put, this is alpha, this is area, here is alpha, and this is this capital F, N1, N2, semicolon, alpha. Okay, so basically what the representation, so a graphical representation of precisely the quantity, the probability that's written at the bottom of the slide is just essentially this area. So you have the PDF, so you have the f-axis, which is the range of support of the associated random variable, the PDF, FF of F, if you like, with lots of F's there, and then basically it's just the area where that capital F, so this capital F here, so capital F, N1, N2, semicolon, alpha, is just the value on the f-axis which corresponds to the fact that the probability of exceeding that point is precisely alpha. Okay, and you can find the values of the F table. So let's have a look. So this is an example. So here what we're told is two things. So we're told the degrees of freedom, 5 and 4, and the level of significance, if you like, 0.05. So now we have our F table. This is the T table. So basically, so you have to be careful with this. This column here is the second degrees of freedom, and this row here corresponds to the first degrees of freedom. Okay, so in our example, we're given 5 and 4. Sorry, 5 and 4. So we have 5 and 4 here. So we have 3 numbers in this cell of the table. And the reason why there are 3 numbers is they correspond to different values of alpha. So remember, in our example, alpha is 0.05. So now we go 5, 4, 0.05 is here, so it should be 6.26, which is the probability of exceeding 6.26 when f has a distribution, a random variable has an f distribution with 5 and 4 degrees of freedom is 6.26. Okay, and that's what it says here, 6.26. Okay, so I just interpreted that statement. And respectively, now if you flip around the degrees of freedom, so now I go 4 and 5, and now our significance level, if you like, is 0.025, then we look at this table, so now we have 4 and 5, and it's 0.025, so it's 7.39, which is the value of the table here. Okay, this is what it says here. 7.39. So the probability, so if a random variable capital F, which is F distributed on 4 and 5 degrees of freedom respectively, then the probability of exceeding 7.39 is 0.025. There's a typo here, just in case you're reading these notes. This should be, say, 7.39, not 0.739. 0.39. Okay? Okay, so we have another result. Just you're going to use these. This is basically nice ways to get at tables. So remember, capital F. So if f is a random variable with n1 and n2 degrees of if f is a value, if we have the f value of n1 under n1 and n2 degrees of freedom at the point 1 minus alpha, then that's the same as doing 1 over flipping the degrees of freedom and alpha. Okay, so what does that mean? What does this statement mean? Well, basically it means this. Okay, let me see if I can draw this nicely enough. Okay, so these are basically points. So basically now, okay, let me just try and, okay, so the result says, so the left-hand side of that inequality, so this probability is 1 minus alpha, and this is n1, n2, 1 minus alpha. So the left-hand side of the equation, right, we know what that means. Basically, that's the point on this f-axis for which the probability of exceeding that point is 1 minus alpha. And this result says now if I draw now the PDF of an f distribution on n2 and n1 degrees of freedom, so I will try and do that here. So I'm now, maybe I'll just put it to the left. Sorry, I'll just put it here. Okay, so now this point here, so now if I draw the PDF, so this is f, and this random variable, this is random variable is 1 over, so this is an f distribution, I don't know, the PDF doesn't look the same, but there's maybe the PDF of an f, n1, sorry, n2, n1 degrees of freedom, random variable. So then basically, if I put alpha here, well, this is 1 over. So this is the PDF of 1 over this thing, and basically this point here is here. So this PDF on your left is the PDF of an n2, n1 degree of freedom. I mean, basically, it gives you a formula to flip from one to the other, if that helps. I mean, that's all it is. So what does this mean? So for example, if you give me n1 and n2 is 10 and 5, and I give me alpha is 0.95, well, if we look at our tables, right, we have 10, what do we have, 10 and 5. So if 10 and 5, and all we have is 0.05, 0.25, 0.01. So at least under this table, so you remember, you can see that there's only 3 numbers here, and it doesn't inside this table we don't actually know the value of f10.5 0.95, but we have our formula. Okay, so our formula says that this thing is actually 1 over f510 0.05. Now this one we probably have. So now we look at our table F10 0.05. So we go F5 10 and 0.05, so that's 3.33. So we have that number, and 1 over 3.33 is precisely my F value that I wanted to compute. Okay, so the point of the theorem is a way to basically expand the size of the table without actually having to expand the size of the table, if you see what I mean. Again, like I said when we started to look at tables, I don't really believe in these things because you do use a computer for them, these things these days, but still, if you need to use a table, you can. Okay, so let's look at a second example related to the F distribution. So we let S1 square, S2 square be the sample variance of independent random samples. Okay, they have size N1 and N2, and they're Gaussian. Okay, so basically we have two IID samples. Sample 1 is IID random variables which are Gaussian with some mean which we don't specify and a variance 10, and the second independent sample which is a collection of independent and identically distributed random variables of size N2 with variance 15. And we're asked to find the probability that the ratio of these sample variances S1 squared over S2 squared is bigger than 1.26. So 1.26 is a special number which is going to make our life easier, and that's the only reason that it's there. Okay, so this is the number that we want. This is the thing I want to compute, the probability that this ratio is bigger than 1.26. Okay, so basically what do we know? So we know that, as we've commented on back here, that S1 squared over sigma 1 squared over S2 squared over sigma 2 squared is F on n minus 1 degrees of freedom, n minus 2 degrees of freedom. So basically what I'm going to do, so my probability is the form almost of this ratio, except I haven't renormalized the numerator and denominator by the underlying variance of the associated random variables. So that's precisely what one does in this probability. Okay, so now I'm going to divide the numerator by 10 and the denominator by 15. And if I do that, I have to do the same thing on the right-hand side of the inequality, which is 15 over 10. So 1.5 times 1.26 is presumably 1.89. Okay, and this random variable here, well, remember that's going to be, as I've just quoted, an F-distributed random variable with degrees of freedom 24 and 30 respectively. Okay, so what do I want to do? I want to compute the probability that F is bigger than 1.89, where F is a random variable which is 24 and 30. Okay, well, basically then we can have a look at our table. So let's see, do we have it? 24 and 30, and if we see immediately we have this value 1.89, so the probability I exceed 1.89 is known exactly, it's 0.05. Okay, so this is the probability that we have as our solution. Okay, so the thing is, this number here, this 1.26 is a special number, as I say, because it's kind of set up so that you can recover the value that your probability you're bigger than this 1.26 from the table. Otherwise, you would have, the only way to compute this one would be to compute the survivor function of this distribution and invert it. The whole point is you can't do that because the function is not available analytically. Okay, so we want to compute these type of probabilities. The only way that we will be able to do it is through the table, even though it's really a task in kind of numerical methods. Okay, so that's the end of chapter 5. I'm trying to go as slowly as I can, but it seems like we still keep on completing things relatively quickly. So we're going to move on to chapter 6. So don't worry, I'll give you plenty of things to do, so we won't run out of things to do, at least not too soon. So you're moving on to chapter 6, which is basically something which is based on estimation based on a normal distribution. So the nice thing about this section is, or this chapter, is we've already seen something relatively advanced. We remember that if you looked at some of the exposition of last week's lecture, we looked at maximum likelihood estimation, which, if you recall, the idea was that you have a sequence of random variables, which are IID, i.e. of a random sample, associated to a probabilistic model, and that probabilistic model has unknown parameters. And our objective in this context was to try to construct an estimator of the unknown parameters on the basis of realizations of our sequence of random variables, i.e. data. Okay, and basically this section is also going to talk about that, although I think at a less technical level really. So we're going to talk about a few things. I'll just talk about basically the things that we'll see today, which are a collection of things, which is point estimation. And point estimation, we have already seen it in a different guise, which was this maximum likelihood estimation. The notion of parameters and statistics, well, parameters we know, statistics we kind of touched on last week. And unbiased estimation, and if we have time, interval estimation. And it's basically all the whole section is really chapter is really interested or concerned with trying to make inferences associated to unknown finite dimensional parameters associated to statistical models. Okay, so let's start out with the introduction. So the nice thing, like I said, is we've already touched upon this before. So we're looking at, assume that some characteristics of the elements of a population can be represented by a random variable whose PDF or PMF is of this type. Okay, so basically what we're going to do is we have, this is a probability distribution of interest. We're going to obtain independent and identically distributed samples which are going to be associated to this distribution, and our objective is to try to work out what the value of theta is. Now this particular section is basically interested in certain types of estimators which are associated to the sample mean and the sample variance of the associated random variables which we observe. Okay. So the form of the probability density function is assumed known, so we're going to have some special form like a Gaussian, an exponential, a Poisson, all these things that we've seen before, but we just want to know what the parameter is. Okay, so it's exactly the framework that we discussed last week with maximum likelihood estimation. So basically the context, as I said, is the same as we have seen before. So the random variables x1 up to xn, which are IID copies of a random variable which has the probability distribution f of x theta, and we have realizations of these random variables. So we see some data, right? So basically this is information. So as you're probably very familiar by now, this is information which are realizations of the model, or i.e. data, and on the basis of the data one is trying to construct precisely an estimator of the underlying probability distribution. Why? Because once I have the underlying probability distribution exactly, I can make inferences. For example, I can predict what the random variable might be in the future. I can, for example, that was one thing you could do with this thing. So basically the point of parameter estimation is central in order to be able to do real life things with your statistical model. Okay, so what we're going to do, as I've stated a few moments ago, is basically, given our observed values, our data x1 to xn, we want to estimate the value of theta. Okay, theta is some parameter vector. Okay, very good. Okay, so the estimation is going to be made in two ways, and we're going to focus firstly on the notion of point estimation. So there are two ways, at least two ways, I think the only two that we're ever going to consider is point and interval estimation. So point estimates are, as we have said and have done already, that is what we find in a value, an estimator, theta hat. So theta hat is written hat because basically precisely it is an estimate which is a functional of the data. Right, and capital theta on the right hand side is basically a function of the data which is random as a function of these capital x1 to xn. Okay, so that's called a point estimator. Okay, and then basically let's see an example. Let's have a look at a couple of examples before we have our break. So basically the question is, well, we know one way in which we can obtain this function of the data. So we've seen maximum likelihood estimates, right, which in our case turned out to be mean and 1 over the mean of the data. But basically these are related to what is known as a statistic, which is basically a function of the data. So a statistic in a kind of non-formal sense is a function of the random sample, i.e. in practice a function of the data. And we can determine that for any collection of data points. So you give me my data and I can give you back the value of the statistic. Okay, so this is should be very familiar to you. So common examples. So we've already seen an example with the sample mean. Okay, so the sample mean is a statistic because if you give me a data set of size n, I can compute the mean. Okay, and that doesn't require the knowledge of any unknown estimator. Another example is x subscript n, which is called the maximum value. Is basically the largest order statistic. So if you give me a set of data x1 up to xn, and you ask me to, and they're all scalar numbers, I can compute the maximum of that. That's a simple operation of cost order little n, because basically the maximum I just compute I take the first one, that's my maximum value, then every time I get a new data point I test whether or not that's bigger than my current maximum, and so basically at the end when I've cycled through all my n data points I can determine the maximum. And these are examples of statistics. An example something which is not a statistic is the estimator, the function w, which is 1 over n, the sum I is 1 to n of xi minus mu square, which looks a lot like the variance, but if I don't know mu, then it's not a statistic because I don't know this value of the statistic, even though I have all the data, even if I have a data set of size n. But if you know mu, of course it is a statistic. Okay, so what we're going to do now, we're going to have a break for 5 minutes. We'll resume at 14:51, and then we'll discuss the mean as a point estimator. Okay, so let's resume. So let's have a look at this. So let's have a look at a point estimator of the mean of a random variable. Suppose mu is the population mean. So what does that mean? No, thank you for saying mean, but what I mean by that, what I want to say, maybe that's a better thing to say, is that mu represents the average value of the random variable. So basically mu, in the notation of this slide, mu is just the expectation of x. Okay, and we've seen that that is either a sum or integral over the support of the random variable. So basically, one way to estimate the mean of a random variable is just to take the mean of the sample, right? You have an independent random, independent and identically distributed samples. They're all numbers, so I add them up and divide by the total number, and that's an estimator of the mean mu. Now, how good an estimator it is, we don't know, or it depends how you depend on how you determine good, but it is an estimator. Okay, and the value that we see, so basically remember that in this language, capital X bar is a random quantity. So X bar is a random quantity. That means that we write it in capital bold capital letters. Okay, and in practice what you see is you observe your data x1 up to xn and you compute the sample value, and we use the notation lowercase. Okay, so the significance of this X bar, which is highlighted in front of you, is that it is a number which you can get on the basis of the data. So if I change my data set, my estimator most likely will change unless I have something funny going on. Okay, so that is a known number, whereas this thing, as we've written X bar, is a random quantity. So there is a difference between the notations. Okay, so let's have a look at an example. I've forgotten what this slide says. So if we have the sample mean of a random sample taken from a population with mean 5, then a point estimate for the population mu is 5. Okay, that's not very exciting. So basically the key point, I don't know if this slide makes one bit of sense, but the key point is that the estimator, any estimator that we choose is a random quantity, so different data sets give you different estimators. I don't know what else you can say about that. So that's our first type of estimator. So there's a point estimate. So basically I want to estimate a quantity, for example the mean of the sample. I compute an estimate, which is for example the mean of the data, and that gives me a number which summarizes the parameter that I want. Another way of trying to do estimation is something called interval estimation. So the idea is you want to construct two statistics. So remember, a statistic is a function of the data and is determinable precisely by that. So the idea is now, well, I'm not going to compute just one number. I'm going to compute two numbers, theta hat L and theta hat U. And explicitly we're assuming that theta hat L is less than theta hat U. Okay. And this interval, the interval between theta hat L and theta hat U, is basically an interval for which the probability of containing the unknown parameter can be determined. So that's what we mean by an interval estimator. So let's look at an example. Suppose we know the variance of a normal, let's say it's a normal sample. Okay, so we have normal IID random variables with some mean and some variance, and we suppose we define theta hat L, which is equal to X bar, the mean of the data, minus 2 times the variance, standard deviation, times square root of n. Okay, this is an estimate, this is a lower value, and this one is the upper value. Okay, and of course I'm not just telling you why that one might choose this as an estimator. It's just a function of the data. I know completely theta hat L and theta hat U if you give me a sample of data, because I'm supposing I know sigma. So then this thing is an interval estimator, and it's an interval estimator because basically I can determine the probability that mu lies in this interval. Okay, when assuming that the data are random, and we will discuss that in a moment. Okay, so this will become apparent why this is an interval estimator. It is an interval estimator. Obviously, this number is less than this number, whatever X bar I get. Okay. Okay, so before we go any further, into this notion of estimation, what we're going to do is we're going to introduce the notion of unbiased estimation. So unbiased estimation is particularly important in many fields, but basically the idea is that basically on average the underlying estimator of my parameter is actually the parameter itself. So this is precisely what this says. I take a statistic theta hat, which is supposed to estimate a parameter theta, and I average over the uncertainty in the observations, and if I do that, I get back the thing I'm trying to estimate. Okay, so here we have two examples of an unbiased estimator. So basically the statement, we're going to prove these results because I think that this is going to be more, it's going to give you understanding of what these things mean. So basically X bar is an unbiased estimator of mu. That is, if I take the average value of this estimator where the uncertainty is with respect to the data, then I get back that the average of this thing is mu. Similarly, if I define S squared as equal to the sample variance, then this is an unbiased estimate of the variance for random samples. Okay. So an example 3, if I define t is basically almost the same as the sample variance, except my normalization is n, not n minus 1, and I take the expectation of this random variable, then I do not get back sigma squared. In fact, it happens to be the expected value of t is n minus 1 over n times sigma squared, which is not equal to sigma squared no matter the value of n for n fixed. Okay. Right, now let's verify these results. So this is some extra work that I've done for you, so because basically we're running out of material, so I want to do some, just at least show you some things. So this collection of notes here, you don't have to worry about the complexity of these things. They are not going to come up in the exam. I'm just going to try and illustrate the ideas, so to give you a complete picture of what the lecture notes are trying to achieve. So this is alumnus. Okay, so it's called mean underscore var underscore ub. So this is basically unbiased estimated of mu and sigma squared. So I'm going to show that basically the results which I've quoted here but not really verified, this 1, 2, and 3, happen to hold in a particular context. Okay, so we take that context of interest. So x1 up to xn is an IID sequence of random variables which are real values, so there's no vector values here. They have a finite mean and variance. That's all we're going to assume. And we define these two statistics, which is the mean of the sample and this variance of the sample with this normalization n minus 1. Okay, and we're going to show that basically the expectation of x bar is equal to mu and the expectation of s square is equal to sigma squared, i.e. that these are two unbiased estimators of the quantities which one seeks to estimate. Okay, and we're only assuming this up to the point where these random variables are just scalars. So for x bar, we have seen the calculation a couple of times already. If I want to compute the expectation of x bar, well, that's basically the expectation. So, I mean, just to add some steps to this lecture notes, if you want to understand a little better, the calculation is fairly straightforward. I'll just write here. There's only a few here, so it doesn't matter. I can write whatever I like. So to justify this first line, what I want to do is I want to compute the expectation E. I'm using this bold E of the mean of this sample. So I want to compute the expectation of 1 over little n, the number of samples, the sum. I is equal 1 to little n of the xi's. Okay, that's the expectation of x bar. Now you remember that in the context of expectations, that if I have a constant multiplied by a random variable, the constant can be removed, i.e. taken outside the expectation operator. And remember then what we have is the expectation of the sum of the xi's. Remember the expectation of a sum is the sum of the expectations. So this quantity here is precisely equal to 1 over n times the sum. I is equal 1 to little n of the expectation of xi's. Okay, and if you can't read what I'm writing, all I've done is just written this line here. Okay, so again, the reason why this is true is precisely properties of the expectation operator. So for those of you who took your midterm this week, you will have seen something like that, or you should have been doing something like that with one of the questions. N was 2, I think, in that case. Okay, now what do you know? Well, basically from the beginning we are told that these xi's are IID random variables and they have the same mean if it's finite. So the expectation of each of these random variables xi is precisely mu. So this number in here, when it is a number, is equal to mu. So we have the sum I is 1 to n of mu, so that's mu times n. Okay? So that's why at the end of the calculation I have 1 over n times mu, and 1 over n times mu is equal to mu. Okay? So that gives me basically what I've done. If you're kind of not really listening to me, basically I've just verified that this is the case for example 1. Okay, now example 2 is a little bit more difficult because basically this operator s square is got the square in it. Now what I'm going to do is I'm just going to verify some preliminary results, and I'm going to use these preliminary results to basically verify the calculation. So again, like I say, if you're not happy with the level of complexity of these calculations, you don't have to be able to do them yourself. I'm just showing you why these results are true. So the first thing I'm going to do is I'm going to look at the expectation of the square of the mean. Why am I going to do that? Because that's something that's going to come into my calculation when I want to compute the expected value of the sample variance. Okay, so basically what is that equal to? Well, then basically that's 1 over n squared times the sum I is 1 to n of the xi square. That's just the square of the mean. 1 over n square is a constant, so I can take it outside my expectation operator. Okay, so now what do I want to do is I want to compute the expectation of the sum I is equal 1 to the xi squared. Okay, and this is not so complicated. It's equal to the right hand side, and you can verify that formula because basically hopefully somebody has taught you this in your mathematical education at some point, and I think I've shown you this result before, but basically this is true for any collection of real numbers, finite real numbers x1 to xn. So I take any reals x1, so I take x I belongs to R for I in the set 1 to n, and I take the sum I is equal 1 to n, 1 to n of xi, and I square them. Okay, and so that's equal to the sum from I is equal 1 to little n of xi square plus the double sum, so this is a double sum I guess, and it's a double sum over the indices where I is not equal to j of xi xj. Okay, so what this double sum means, this thing here, equivalently, I've just written it like this here, it means I sum over all pairs I and j where I are not equal to j. So like, for example, I sum from I is equal 1, 2, 3, 4, 5, 6, 7, 8, 9, and then if n is 10, I just allow j to equal, if I is equal to 1, then j goes from 2 to 10, and so on and so forth. Okay, so this result is true for any finite real numbers. It's nothing too complicated. You can verify in the case n is equal to that this result holds, because if you multiply x1 plus x2 all squared is x1 squared plus x2 squared plus 2x1 x2. Okay, and you will get that exactly from this equation here. Okay, now in our scenario, the x's represent random variables. So now what I want to do is I want to compute the expectation where these xi's are random quantities. Okay, and so the expectation operator basically means I've just split it over two of these two operations. Okay, that's all you've done, all I've done here. Okay, now the expectation of xi square. Well, remember what we have been told. We know some information, okay, and that information is that the random variables have a mean and a variance. So if I know the mean and I know the variance, I can determine the second moment. So we are told the following. We're told that the expected value of xi for every I is equal to mu, and we are also told the expected value of xi minus mu all square is equal to sigma square. Okay. Now, if you use these two equations, this equation 1 and this equation 2, you can easily determine the expected value of xi all squared. So this implies, if you solve, so this is going to imply that the expected value of xi square is equal to mu square plus sigma square. Okay, this is true. You can easily do. I think we've even done it in the class. Okay, so why is that interesting? Well, that's interesting because in this bracket here, this term for every I is mu squared plus sigma squared. So this becomes, because this is sum, I get n times mu squared plus sigma squared. Now for this term, in this term, I have the expected value of xi and xj, and I is not equal to j. So we know that the random variables xi and xj are independent. So the expected value of xi times xj is just equal to the product of the expectations, okay? And precisely from the fact that the expected value of xi for any I is equal to mu, this product of expectations is the square of the mean, okay? So this summand is precisely mu squared, and the number of summands is n times n minus 1, okay? Because this operator here is the double sum. So I get n times n minus 1 mu squared here. Okay, and then I can take out a factor of n, and that's my first equation. This gives you an expression for the expected value of the square of the mean. Okay, and why do I need it? We'll see in a moment. Okay, and like I say, if you're lost, you don't like these things, it's not really needed in the exam. I'm just trying to show you that these things these calculations lie well within your expertise. It's just that we choose not to do that to examine you on them. So a second result which we're going to need is the following. So I fix the index I in the set 1 to n, and I consider the expectation of xi times x bar. Okay, so that's, remember, so the xi times x bar is xi times the sum j is equal 1 to little n of xi's over little n. Okay, so that means that when I compute this expectation, I can take a factor 1 over n outside of it. Now, basically, only thing I really care about when I look at this product is the case where in this sum I have j is equal to I, and when I don't. When I have j is not equal to I, then this product is basically the sum over all j's for j not equal to y of the expected value of xi times xj. But if j is equal to y in the summation, I get xi, so I get the expected value of xi squared. Okay, this quantity is, we've already worked it out, that quantity is mu squared. So there's n minus 1 of these, so I get n minus 1 mu squared. And this one we've already worked it out. It's mu squared plus sigma squared. So this expression is 1 over n minus 1 mu squared plus sigma squared. Well, we'll just leave it like that. Okay, now what's the point? The point is, what I want to do is I want to compute, what I'm trying to do is just to keep, just to close the file. Sorry about that. Sorry, where are we? Here we are. Okay, so what we're trying to do is to verify that the expectation of the random variable s square is precisely equal to sigma squared, i.e. that it is indeed an unbiased estimator for the variance of the sample. Okay, so in order to verify that, so this is just these calculations. So I want to compute the expected value of s squared. Okay, s squared we know, that's equal to 1 over n minus 1, the sum I is equal 1 to n of the xi minus x bar squared. So if I compute the expectation of this expression, I can take the factor 1 over n minus 1 outside. Now xi minus x bar all squared is xi squared plus x bar squared minus 2 xi x bar. You know how to multiply out quadratic. Okay, and if I take the expectation of the sum, that's the sum of the expectations. So that's where I get this result from. Okay, that's all you have to do. And now what do you do? So you can now break these three expectations into a sum of three expectations. So at the expected value of xi squared, that stays. The expected value of x bar, well, the expected value of x bar squared is the same for each I. Remember, I've got a summation here, so I get n times this quantity here. Okay, and this is minus 2 times the sum I is 1 to n of the expected value of xi times x bar. Okay, so now if you look at this line here and you analyze the two results we've derived up above, we'll see these two results become directly relevant when now computing this quantity here. So this one, we have already calculated it. So n times the expected value of x bar squared, well, that's just n times this quantity here. So I get mu squared plus sigma squared plus n minus 1 mu squared. Okay, that's this term here. This one, sorry, I made a typo here. Yeah, this one's right. This is not correct. This one should be, so this is, the expected value of x squared is mu squared plus sigma squared. Okay, so this one is not n mu squared, there's a missing plus sigma squared here. So this is a typo, sorry about that. And now the expected value of xi times x bar is 1 over n this times this. So basically now this quantity, I put it in here, so I'll get 2, and you get n of them because these are the same for each I. And so this is this term here. So I will correct this slide later today. Okay, and basically you get this expression here at the end. And if you do a little bit of algebra and you remove my mistake, you'll get that basically this term here is equal to n minus 1 sigma squared times 1 over n minus 1, which is equal to sigma squared. Okay, so the expected value of x squared, s squared, is exactly sigma squared, and I'll correct the mistake later on today. And the key point is, in this calculation, you can also deduce the factor 1 over n minus 1 has been effectively removed. So basically the calculation, if you follow it and you replace s squared with this quantity t, then basically if you follow this calculation here, what you'll get is 1 over n here, and this will be n minus 1. So you'll get n minus 1 over n times sigma squared, which is precisely this result here. That is to say that it's a biased estimator. Okay, so again, this calculation that I've given you is a typo in it. This is n mu squared plus sigma squared. So I'll put that in later. Okay, but that's just verifying these results, that basically an unbiased estimator is one for which the average value with the uncertainties with respect to the observations gives you precisely back the parameter that you wish to estimate. So in this scenario, basically the mean is an unbiased estimator for the mean of the population. The mean of the mean of the variance estimator with the normalization n minus 1 is unbiased, which is why people tend to use it. And this one actually is biased, as what I've shown just a moment ago. Okay, so this is a property of estimates. So this also often gives you a justification for using an estimator. So if x bar is unbiased for mu, it seems that x bar is a reasonable estimator for mu. There are many other considerations, but that's one that you can use. Okay, and so that's point estimation. I don't think we do anything more on point estimation. It's amazing. Yeah, this is that's the last. So that's the last we see of point estimation. I'm amazed. Okay, so that was point estimation. I will return to that when we get finished with these notes, because I don't think there's enough on that. Okay, so let's now. So in practice, what we're going to work a lot with apparently in this course is interval estimation. So this is another way. So instead of giving me back a number, I have a range of numbers which provides us a kind of a degree of uncertainty associated to our point estimator. So we can provide a point estimator or a parameter, mu, let's say the mean, but we may also be able to understand or want to know how uncertain we are associated to this estimator. So an estimator, as we said in interval estimators, is a form an estimate of a population parameter theta, where we have two limits, theta hat L and theta hat U, where theta hat L is strictly less than U. And theta hat L and theta hat U will depend on the value of a statistic of a particular sample and the sampling distribution of theta hat. Okay, and if this statement seems very unclear at this stage, then I will explain them at the moment. So the interval estimate, it works like this more graphically. I think this is a nice plot. So you have your point estimate, theta hat, your mean of your sample. Okay, and basically this point here is your theta hat L, and this is your theta hat U, and this is the width of your confidence interval. So of course, if you have two estimators and you construct two different interval estimators, and we'll see how to do that in a moment, and one is very narrow and one is very wide, then you tend to believe that the first one with the small confidence interval is kind of a bit more of a useful estimate than the one with the wide confidence interval. And we're going to see, we're going to understand that statement in a moment. So we note the different samples, so we have a different data sets, will give you different estimators. Basically, this is the reason why these confidence intervals are useful. So different values of theta hat L and theta hat U are basically, that basically means these things are random variables in the data, and these intervals may or may not contain theta, as theta hat and theta L u vary. It's very useful. Let's formalize. I think this slide should start here a little bit more. So what we're trying to do is the following. We're going to try and obtain these lower and upper bounds of the confidence interval theta hat L and theta hat u, which are going to contain the parameter theta, the true parameter theta, population parameter, with probability 1 minus alpha. That is to say, when taking into account the randomness of the observations, the probability that basically theta lies in our interval is going to be of order 1 minus alpha, where we choose alpha ourselves. And this is what's meant by a confidence interval. So I think this is a bit more, this is basically the cleanest statement you can have of this type of statistics. So the probability that when you take your interval estimate, what that is, we're going to have to find out. The probability that the true population parameter lies in the interval can be made, or is arbitrarily large. So obviously, if you make alpha closer and closer to 0, you expect that this interval to be larger and larger, because basically you're more certain that basically the estimate, the population mean, lies in the estimate in the interval. Okay, so the interval is computed from a selected sample. It's called the 1 minus alpha 100% confidence interval. Okay, that means, so alpha you choose it, let's say 0.025, so then that's a 97.5% confidence interval if alpha, and alpha is 0.5 is a 95%, and the fraction 1 minus alpha is called this confidence coefficient. I prefer that phrase. And the end points, theta hat L and theta hat U, are the lower and upper confidence limits respectively. Okay, very good. So this basically means the following. If the sample size of n is taken, if you do that repeatedly, so I've got 100 samples, I do that 10,000 times or many times, then basically in the long run, so the more times I take these sample sizes, basically with this, in this percentage, basically with 1 minus alpha 100% of the time, you will contain the true parameter. So I have a sample size of 100, I do that 10,000 times. If alpha is 0.05, then 95% of the time, my confidence interval will contain theta, the true value. Okay. I mean, I don't believe in these statements, because basically this whole thing here, just to explain to you, this whole statement at the beginning is taking randomness with respect to the observations. But the point is here that the observations are actually seen. We see the data. So it seems not to make any sense to average over the uncertainty in the data when that's something we observe. But this is the way in which some statisticians have decided to construct confidence intervals. I don't find this a useful plot. So let's have a look at how we can actually do this. So we're going to look at the first, I think we'll just look at one example. I was going to look at two, but I think I will run out of time, so I just want to look at the case of the following. So we have the following case. We have a random sample, so a selection of IID samples, where we know the variance, okay, so you have to suspend your disbelief, and the population is normal. Okay, or n is sufficiently large, at least 30. So remember, by the central limit theorem, we can justify the fact that for large samples, basically the population mean is approximately Gaussian in some way. Okay, so basically IID random variables where either they are Gaussian or we're going to apply the central limit theorem, and the variance of the sample is supposed to be known. Okay, so so we know that we saw a week or 2 weeks ago that the mean of a random sample is either exactly or approximately Gaussian distributed with a mean mu and a variance sigma square over n. Okay, we know that. That's something that we have seen. You can go back in your lecture notes and read it. We have talked about it, watched the video and watch me talk about it. So what we know then is basically if we standardize the random variable capital X bar, i.e. we subtract the mean and divide by the standard deviation, that this random variable here is normal 0, 1. So what is it we're trying to do here? What am I trying to describe to you? I'm trying to construct a confidence interval for the mean of a Gaussian sample, or the mean of the sample, essentially. Okay, so now we know that x bar minus mu over sigma over root 10, that's normal 0, 1. So the probability that it lies between these points z alpha over 2 and minus z over alpha over 2 is 1 minus alpha. So what does this statement, what are these numbers? So if you have forgotten this notation, so let me just remind you what these numbers z alpha over 2 and z minus z alpha over 2. So remember that the Gaussian distribution is this kind of symmetric bell-shaped curve. So the PDF looks like this. So we have the random variable, let's call it z, and then this is the PDF f z of z. Okay, and the PDF looks like this. Okay, rough supposed to be symmetric, and these numbers z of alpha over 2. So I put this here. This is z alpha over 2, and this area here is alpha over 2, and here is minus z alpha over 2. And this area here is alpha over 2. Okay, so these numbers z of alpha over 2 and minus z over alpha 2 represent the points in the support of the random variable for which the probability I exceed z of alpha over 2 is precisely alpha over 2, and the probability that I'm less than minus z over alpha 2 is alpha over 2. So this is supposed to be alpha over 2. Okay, and this is what these 2 points mean. Okay, and in our context, the statistic x bar minus mu over sigma over root 10 is precisely Gaussian distributed. So this is the distribution of the statistic, and we know the distribution of the statistic precisely from our results that we have established in the previous chapters. I think the previous 2 chapters. Okay, right. So now what can I do? So now I can take this quantity sigma over root 10. I can multiply both sides of the equation, inequality of it, and then I basically subtract the mean from both sides and multiply by minus 1. And if I do that, the probability that the mean lies between these 2 points, x bar plus z alpha over 2 times sigma over root 10, and is bigger than sigma over root 10 times minus z alpha 2 times x bar, is exactly 1 minus alpha. Okay, so this 1 minus alpha, remember that this area, those 2 shaded regions are alpha over 2, so the area in between those 2 points is exactly 1 minus alpha. So this 1 minus alpha is come from this construct where these 2 points are z or alpha. So this is the area that we're computing, actually. These 2 areas are representing the complement points. Okay, now what is the point? Why is this equation at the bottom of the slide labeled? Well, it's labeled precisely because this provides us a confidence interval of level 1 minus alpha 100%, because basically we're guaranteeing that the probability that the population parameter mu lies in this interval is exactly 1 minus alpha. It's exact. Well, it's exact only. Of course, this equation here is only exact in the Gaussian case, and otherwise we're applying the central limit theorems. Otherwise, we have an approximate equation. This is approximate. So basically, to summarize, the thing that we've derived, we haven't had to do too much work to do it, is if x bar is the mean of a random sample, IID random variables, which is large enough, and we have under our knowledge the fact that we know the variance of the sample, then a 1 minus alpha 100% confidence interval for the mean of the sample is precisely, that's not given that. This is the lower bound, x bar minus z alpha over 2 sigma over root 10, and this is the upper bound, x bar plus z over alpha over sigma over root 10. Okay, so the sample size for estimating mu, okay, so most of the time x bar is not exactly equal to mu, and the point estimate is of course in error, right? What does that mean? That means that basically I estimate the true sample population mean, I estimate the true population mean with the mean of the data, and the mean of the data is not likely to be equal to the mean of the population mean. There's going to be an error, okay? And we can classify this error at least in one way, which is the absolute difference between my estimator and my true number, mu. So we know that already. So what the calculation we just did is the probability that x bar minus mu is in this interval is 1 minus alpha. That's just a rewriting of this equation. Okay? We know that. Oh, sorry, I've just got the wrong equation. We know that. Okay? Now, this is a two-sided thing. So this statement here is equivalent to the absolute difference of x minus mu being less than z alpha over 2 sigma over root 10. So what I'm saying is that this statement here, forget about probability, this statement here, which I'm trying to highlight in blue, is equivalent to this statement here. Okay, so the collection of x which for this is true is the same as the collection of x for which this is true, so their probabilities are equal. Okay, so why is that interesting? Well, the key point is that this is our error that we are talking about, and that's the difference between the true population mean and our estimate and the absolute value of it. Okay, so now we denote, so E is the margin of error, and we'd like the margin of error, that is the margin of error in our estimate, to be not to estimate, so we want the error, what is it? What we want the error does not exceed the margin of error E. Oh, so we want the probability that the error. Okay, this statement is completely wrong in English. What we want to do is we want to ensure that our error E, let me say this right. You choose an E. Okay. Now I want the probability that my error is less than E to be at least 1 minus alpha. Okay, so this is confusing, it's completely confusing, so forget about this statement here. I choose little e, I want that to be my error, and I want the probability that this error is less than or equal to e is at least 1 minus alpha. Okay, right, now, so since the probability that x bar minus mu, which is my error, is less than z alpha over 2 times sigma over root 10 is equal 1 minus alpha. So basically I want the E that I choose to be bigger than this. Okay? So if you give me my E, I can determine my sample size for which this is true. So you choose E. Okay, I know sigma, I know z alpha over 2, so I can rearrange this equation. So if I rearrange this equation, I get n, I divide by e, and I square both sides. So basically, the number of samples I need, little n, to achieve a given pre-specified margin of error is of this size. Okay, so this tells you how good your parameter estimate is, or how large a sample size you should collect in order to ensure that your estimate of the mean, which is the mean of the sample, is within a pre-specified error. Okay, so this is a kind of inverse type thing. I choose the amount of error that I want, and then in order to achieve such an error, I have to collect a certain size of data. Okay, and this is the size of data that I have to obtain. Okay, so we're going to look at one example. I think that's it for today. Okay, so the mean of the mean CAP of a random sample is 36 college seniors is calculated to be 3.5. Okay, so that's CAP, not GPA. And we're assuming that we know that from previous studies that the variance of the standard deviation of this CAP is 0.3. So we're asked the two questions. One, I want to find a 95% confidence interval for the mean of the entire class, and we'll think about 2 in a moment. So point 1, so a 95% confidence interval for the mean mu. Well, let's remember is basically the mean of the sample minus now z 0.025, I want 95%, so this is z of alpha over 2, so 0.025, and x bar plus z alpha over 2, sigma over root 10. Okay, so the only thing here, we know sigma, that's 0.3, okay. I know alpha is 0.025, that's given from here, okay, and I know the mean is 3.5. Okay, so I know all the numbers, and the only thing is to find z of 0.025. Well, that's 1.96, and if you're wondering where can you get that, okay, where is this? This is the binomial distribution, this is the Poisson distribution, and we have the normal distribution. Okay, so now, okay, so now what do I want to find? I want to find the value 0.05 in this table, okay. So basically, 0.025. So if I go here, I get 0.96, and this value here is 0.025. That's exactly the number I want, and that corresponds to 1.96. Okay, so this is 0.06, this is 1.9, this is 0.0250, which is exactly giving me this number here, 1.96. Okay, and so now I plug my numbers into my equation, and this is my confidence interval of level 95% confidence. Okay, so now example 2. So this is this idea that I want to determine my sample size in order to find a pre-specified error on my associated estimator of the sample mean. So I want to know how large a sample is required if we want 95% confidence that our estimate mu is off by less than 0.05. So here this is giving you the value of E is 0.05. Okay, so we're basically going to plug in 0.05 here. Okay, so n must be at least z alpha over 2, that's 1.96, that's our 95% thing. Sigma is 0.3, E is 0.05, and I square it, and that's equal to 138.3 apparently. So what does that mean? It means that I need at least 139 individuals to ensure that the sample that ensure that basically 95% confidence that our estimate is off by less than 0.05. And off, what that means is basically that this error here is at most 0.05. Okay. And that's the end of the example. So we don't have time to cover it in any kind of totality today. So what we're going to do tomorrow and later on is to investigate the scenario where the variance of the sample is unknown. Okay, so that's it for today. So I'll see you 2 o'clock tomorrow. Thanks for your attention.